Hi, welcome back to the IPC Essentials. We are going to be covering waves today, so Unit 7 dealing with waves. And there's a lot to cover with waves, so let's go ahead and get right to it. So we're looking at the topic of waves. And so what is a wave? What does a wave do? Well, a wave has one simple job, and that job is to transfer energy. This is a big thing. Energy is a big thing in physics. And so energy is able to get from one point to another point through means of waves. And so there's two types of waves. There's mechanical, that's the first type, mechanical. And the second type is this thing called electromagnetic waves. So electromagnetic, also known as EM waves for short. So there's mechanical waves and there's electromagnetic waves. And so the first thing we want to look at is mechanical waves. Well, really, what is the difference between the two? The difference between the two is that mechanical waves require a thing called a medium. So mechanical waves require a medium. Electromagnetic waves require no medium. And so then you may be asking yourself, well, what is a medium? A medium is something that you have to travel through. You have to travel through it. And so take, for example, a water wave. A water wave is only made possible with water. The wave is able to move through the water. The water is the medium. An earthquake. An earthquake needs a medium to be able to travel. So an earthquake is a bunch of waves. Waves are transferring energy, so that energy is being spread out. And what is that traveling through? It's traveling through the earth. That's why we have an earthquake. So medium is something that you have to be able to, you have to have something to travel through it. That's a mechanical wave. Electromagnetic waves do not need a medium. Electromagnetic waves can travel through space. Out in space, there's no air. So let me give you an example. If you have the sun out here, right, here's the sun, and then you have the earth over here. Well, what's in between the sun and the earth? What is out here? It's a bunch of nothingness. It's just space. It's called a vacuum. It's called a vacuum. That means that there's nothing out there in space. But yet light is able to travel from the sun to the earth. Right? Light is able to travel. So light is an electromagnetic wave. It's able to travel because no medium is necessary. Okay? Okay. So let's focus on mechanical. Some examples of mechanical waves would be, like we've already stated, water. Sound is the big one, and we'll talk about that one. Sound. Water waves, we said earthquakes. We'll just put EQ for earthquake. So these are some examples of mechanical waves, something that you need, you have to have a medium, something to travel through. Okay, so let's focus on mechanical. So there are two types of mechanical waves. So let me actually leave it here. So there are two types of mechanical waves. One type is called a transverse wave, and the second one is called a longitudinal. So there's a transverse wave and there's a longitudinal wave. So what is the difference between a transverse mechanical wave and a longitudinal mechanical wave? It has to do with the way that the wave travels in relation to the medium. So What we mean is that if you have a transverse wave, it's going to look something like this. Okay? So what's happening here is you have particles. Right? If I just pick a few particles anywhere along this line here, the wave is going to be traveling from left to right. So as the wave travels here and it moves across to the right, the wave moves to the right, but these particles are not. What's actually happening is these particles are moving up and down. And it doesn't matter where it is. They're moving up and down. They're moving vertical while the wave moves horizontally. Okay? So if we had an earthquake, right, the earthquake would be moving from, from the epicenter to a city or a town or something, right, from point A to point B. As the wave travels, the particles are only moving up and down. Okay, so what's happening is that the particles move perpendicular. So the particles move perpendicular to the wave. That makes it a transverse wave. For a longitudinal wave, you're going to have a wave that travels to the right, but the particles are also going to move to the right. Right? They move parallel. For the transverse wave, we have the wave moving from left to right, but your particle motion is perpendicular to that, like we have here. So usually when you see a longitudinal wave, you have something that looks like this. You have particles bunched up together, and then the particles spread out. The particles bunch up together, the particles spread out. And so this is what the wave looks like. This is our transverse wave. This is our longitudinal wave. Okay. So if we label these here in a second, you'll see that this matches up with the trough. This is going to match up with the crest, and so on. So let's go ahead and do that. Let's label these two things. The main one that you're going to see is a transverse wave, something that looks like this. So if we were to label this transverse wave, there are points on here that we're going to focus on. One of them is going to be the top part of the wave. That's known as the crest. The bottom or lowest part of the wave, that's going to be called the trough. You have a point from the highest point to what we call the 0 point or equilibrium. This is going to be your amplitude. This is most close to the closest to energy. So think of the amplitude of the wave as the amount of energy that's held within that wave. So far we have the crest, we have the trough, we have amplitude. The other point that we want to focus on is from one point to the next consecutive identical point. So from here to here is going to be what's known as wavelength. Wavelength. Okay? And wavelength can be from crest to crest. It can be from trough to trough, as long as the points are identical and they are in consecutive points there. So crest is the highest point, trough is the lowest point, amplitude is the amount of energy that goes from the middle to the either highest point, or it could be the lowest point. Most often you'll see it to the highest point there. And then wavelength is from crest to crest, from trough to trough, or from the middle of the wave to the next middle part of the wave. All right. So let's take a look at some characteristics of waves. We have reflection. We have reflection. We have diffraction. We have interference. Oops, interference. And we have, let's see, we said diffraction. So reflection, diffraction, interference, and refraction. So we're going to take a look at each one of those. For reflection, reflection is going to be bouncing of waves. So waves can bounce off of a surface, right? They can bounce back. And because of this bouncing back, you have interference, which we'll talk about here in a second. So think of reflection, bouncing of waves. Think about your reflection bouncing off of a mirror. Diffraction is where you have light waves that bend around openings or around objects. So if we had, let's say, a river, and you had something in the middle of that river, let's say a boulder or something, these waves would come in, and what happens is they'll bend around that wave, and then they'll come together like this. Okay? Or they'll bend around a corner or an opening. The diffraction is the bending of the waves as they go around objects or around corners. Refraction is bending of light. So bending of light. Refraction is bending of light. And then interference is the big one that we want to focus on. There's two types of interference. There is constructive, and then there is destructive. So constructive interference and destructive interference. Constructive interference is, think of it as you build a bigger wave. Think of it that way. You build a bigger wave. Destructive is you make a smaller wave. Think of it that way. So constructive interference is where you're going to build a bigger wave. Destructive interference is going to be where you make a smaller wave. So let's say that you have two waves coming together. Let's say you have this wave is coming this direction, and you have this wave coming in this direction. Okay? So let's call this wave A. Let's call this wave B. So as A and B start going towards each other, there's going to be a point where they actually interact with each other. And at that point, right, at that point, the wave is going to get bigger as they interact. And so you get A plus B at this particular point. After that, the waves are going to continue on as they pass through each other. But right here, there's constructive interference occurring. For destructive interference, if you have one wave coming, let's say that's A, and then you have a wave coming in this direction, let's call this B, as they start going towards each other, they're going to build a smaller wave. And actually, if these two were the same amplitude, as they come together, they're going to cancel each other out, and you would get something that looks like this. So notice that you've made the wave smaller than either one of these would have been. That's interference of waves. This is the idea behind noise cancellation headphones. Right? You build smaller waves. Constructive, you build bigger waves. Okay? So those are some properties of waves. Another thing that we want to talk about specifically, because sound is a mechanical wave. Sound is a mechanical wave. So there's a couple of things that we want to look at that with sound. One is how fast the sound travels. If you wanted to figure out how fast sound travels, we could figure out the speed of the wave. So wave speed is going to be equal to the frequency of the wave times the wave length. We've already looked at what wavelength is. We want to talk about frequency here in a second. So the wave speed is equal to the frequency times wavelength. So if we want to abbreviate that, we could say velocity is equal to frequency. The symbol for wavelength is this upside down looking Y. That stands for wavelength. So wavelength, we already discussed, is what the distance is from either crest to crest or from trough to trough or from midpoint to midpoint. That's wavelength. The frequency is how often, so we can write this, how often the wave occurs. So frequency is how often the wave occurs. And if we want to figure out the wave speed, we simply do frequency times wavelength. So an example of that would be 180 hertz, which is the units for frequency, times, let's say, a wavelength of 2 meters. So if we wanted to calculate that, we simply do 180 times 2, which is going to give us 360, and that's going to be in meters per second. So that'll allow us to figure out what the wave speed is. Where does sound travel fastest? Well, there's 3 types of matter. There's solid, there's liquid, and there is a gas. So for solid, liquid, and gas, where does sound travel fastest? We have to keep in mind the particles. So in a solid, the particles are going to be really close together. In a liquid, they're going to be a little bit further apart. And in a gas, the particles are going to be spread out the most. So remember, sound is a mechanical wave. Mechanical waves need a medium to travel through. The medium are these particles here. So sound travels whenever one particle hits another particle, that particle hits the other, and that particle hits the other. So the closer the particles are together, the faster they can transfer that energy from one to the other. If they're farther apart, that means it takes longer to get that energy from this particle to this particle to this one. So sound travels fastest here in a solid, and it's slowest here in a gas. Because the particles are spread out further here, it's going to travel slower. Because the particles are closer together here, they're going to travel the fastest. The other thing that we want to talk about with sound is this idea of pitch. Pitch is going to be the highness or the lowness of the note. So the sound that it makes, how high it is or how low it is the pitch. A high note or a high sound has a high pitch. A low note has a low pitch. So highness and lowness is called pitch. And then associated with this is called the Doppler effect. And you have probably heard this occurring before. The Doppler effect is when it sounds like the pitch of a car or a train or a bus or something that's laying on the horn. It sounds like the sound changes as it comes towards you and then as it passes away. That's known as the Doppler effect. If you're standing here and you have a fire truck, call this a fire truck, right? If this fire truck is coming towards you and it has the siren on and it's putting out sound, right? That sound is going to hit your ears. So as it's coming towards you, these wave fronts bunch up, and as they bunch up, the frequency increases. So a high frequency, remember we talked about frequency. Frequency is how often the wave occurs, right? Frequency is how often the wave occurs. So if it's coming towards you, the frequency is going to be high. So a high frequency means that you have a high pitch. So that's as it's coming towards you. As it passes you and starts to move away, the wave fronts are going to start to spread out. So that means that the frequency is going to decrease, which means that the pitch is going to decrease as well. And so it sounds like it's changing its frequency, but it's not actually changing its frequency. It just depends on the frequency, right? As it comes to you, those wave fronts are going to be closer together. And then as it moves away, those wave fronts are going to be further apart. That's the Doppler effect. Okay. So that's sound. Remember, sound is a mechanical wave. Now let's quickly talk about EM waves. So there are radio waves, there are microwaves, infrared waves, there's visible light, there's ultraviolet, there's X-rays, and there's gamma rays. So these are the types of things that you would find in the electromagnetic spectrum. This is what we know as light. In fact, all of these things are light. Every bit of this is light. Radio waves, microwave, infrared, violet, ultraviolet, X-ray, gamma rays. All of those things are light. So the thing that we most often think of light is the visible light spectrum, but uh, that's just part of it. You have to include all of these things as light because all of these things travel through particles known as photons. These photons are responsible for all of these things here. Um, so let's just look at color for visible light. How does color occur? How do we see color, or what is color? Let's say that we have a green object. It doesn't matter what it is. It could be a leaf on a tree or something. If you have a green object, why does that thing occur, or why do we see it as green? So when we talk about visible light, light from the sun, light comes in and it's called white light. Okay? White light. White light will strike an object. But the thing with white light is that it's composed of all of the colors of the rainbow. What you know as red, orange, yellow, green, blue, a blue called indigo, and then violet. So all of these colors actually make up what we call white light. So all of these colors are traveling in white light. It strikes the object, and when it strikes this object, this green object, what we see as green, it's going to absorb all of the colors except for green. Green is actually reflected off. There might be some slight other colors, but green is the color that's reflected off in what we see in our eye here. So here's our eye. We see the green light being reflected off of this object, while it absorbs the red, the orange, the yellow, some of the yellow, the blue, and the violet. Those things are absorbed, and we're seeing the reflection of the green light off of that object. Okay? If we were to look at a white object, why does something appear white? Well, if you have white light striking that object, remember, white light is composed of red, orange, yellow, green, blue, indigo, and violet. If white light strikes that object, then what you get is white light bouncing off of that object. So all of the colors are going to be reflected off of this object. You have red, orange, yellow, green, blue, indigo, and violet. White light strikes the object, white light bounces off. All of the colors are bouncing off. As opposed to here, where we only had one color, green, bouncing off of that object. The other thing is, what if we see a black object, something that's completely black? What's happening with it? Well, if you have white light striking that object, white light strikes that object, what it does is it absorbs all of these colors of light. It's absorbing red, orange, yellow, green, blue, indigo, and violet. Nothing is bouncing off of that, so we don't get any colors hitting our eyes. And so what we see is the absence of color when we look at something that's black. Okay? White light, we're seeing all of the light. Black light, we're not seeing any light being reflected. If we see something with color, we're seeing those colors bouncing off of that object. And so our brain interprets those colors there. The other thing that I wanted to talk about with color is this idea of diffraction. So earlier on, I talked about diffraction as being a thing that happens with waves. Refraction is bending of light. Light can bend. So Diffraction occurs when we see a rainbow. So if we have a raindrop, right, this is just a single drop of rain. Remember, we have white light. And what was white light? White light was red, orange, yellow, green, blue, indigo, and violet. That was all of the colors that are part of white light. So as the white light passes through a raindrop, you have this light bending because white light is composed of all these colors, and each one of these colors is going to have a different amount of energy, right? They have a different speed. So the higher energies are going to travel faster, lower energies are going to travel slower. Violet has the highest energy, red has the lowest energy. So white light strikes the raindrop. The raindrop is going to act like a prism, which is going to separate white light into its component colors. So what happens is it bends, and as it bends, red goes slower. You have orange next, yellow, green, indigo, and violet. So all of the colors actually bend out of it. So you have red, then you have orange, then you have yellow, green, blue, indigo, and violet. So each raindrop acts as a prism to separate white light into its component colors. And so what we see in the rainbow is just raindrops, little droplets in the air, separating white light into its component colors. So that was just another example of refraction, which is bending of light here. Okay, so I think we've hit most of the basic ideas dealing with waves. Remember, mechanical waves require a medium. Electromagnetic waves do not need a medium. Sound is a mechanical wave. Light is an electromagnetic wave or an EM wave. Sound is a mechanical wave. Radio waves, like I said earlier, are electromagnetic waves. They're part of the electromagnetic spectrum, right? So here's radio waves. So a sound wave is not a radio wave, something to keep in mind. Okay, hopefully that helps, and we'll see you in the next part of this.